Let's look at section 3.2, polynomial functions and their graphs. You can read through the learning objectives there. It's always a good idea to read through the chapter before you listen to or look at my videos, because my videos just give you kind of the mechanics of going about the different operations and procedures and patterns we'll see with these, but the book gives you some really great applications, and I try to hit an application from each section on the type of function we're discussing, but it's always good to read your book. So let's look at how a mathematician would write the general form of a polynomial function. It looks kind of complicated, but all it's saying is this. We have a polynomial function that's going to take this format. F of x equal a to the n, x to the n, plus all this other stuff. All that's saying is if you have a polynomial function, it needs to be in descending powers. Your highest power first, then -1 means the next power is 1 less than that at least, and so on all the way till you get to a constant. A quadratic was just a special form of a polynomial function. It was a squaring. The highest degree was 2. So a quadratic is just a special type of polynomial. So when we're looking at polynomial functions, this first term, when it's in descending power, is called the leading term. And the degree on that leading term tells you the degree of your polynomial. So since it's a degree of 5, it's a 5th degree polynomial function. Notice that the degrees are in descending powers, highest power to lowest power. Our last term there is a constant. Quadratic, again, was just a special form. First thing is, let's see if we can decide if something is a polynomial function or does not represent a polynomial function. So y equal 2x plus 3, yes, that's a polynomial function. Follows the general rules that we have written up there about a polynomial function. All of your coefficients here are integers, or they could actually be rational numbers, or real numbers. We should just go ahead and say that they're going to be real numbers. The deal is you can't have any fractions, divisions of your variable like x cubed in this case. That's what I'm trying to get at. So here is a function. It does not represent a polynomial function because we have this fraction format. Here we see just a basic quadratic that we saw in the previous section. Yes, it's a polynomial function. And there's actually a typo here. This should have been a plus. But because this one has a fractional exponent, it is not a polynomial function. So fractions within are fractional exponents. It won't be a polynomial function. The one that I have mentioned up there, the one that I have mentioned here, 5th power, 4th power, 2nd power, so on. It's in descending powers. Yeah, that's a polynomial function. When we graph these, we will always see the characteristic of a polynomial function's graph to be a curve that is smooth and continuous. Like a parabola. A parabola was a nice smooth curve. Polynomials, the higher the degree, the more hills and valleys we're going to see. So let's first talk about end behavior. When we're asked to determine end behavior, we're trying to determine the behavior of the graph of the function to the far left and to the far right. And the end behavior for a polynomial function can be modeled from or by the leading term. However the ends of that leading term would behave is how the ends would behave for the polynomial function. If the leading term is an odd degree, then the ends will have opposite behavior. If the polynomial is an even degree polynomial function, that first leading term is an even degree, then the ends will behave the same. The end behavior will be the same. Let's just kind of do an overview of this leading coefficient test that will tell us our end behavior. It's saying, okay, first case, n is odd. Think about x cubed. If you know the way x cubed behaves, which looks like this, where the left end goes down and the right end goes up, Well, it doesn't matter if it's a cube or a fifth or a seventh power, the ends will all behave in that same fashion. The left will go down, the right will go up. What if the coefficient in front of that is negative? Then it's just the x cubed that's been reflected across the x-axis, and the left goes up and the right goes down. If you understand how these two look, that's what this is saying. This is saying if the coefficient up front is positive, like we see for this, then the left end will go down, the right end will go up. If the front coefficient is negative and that degree is odd, then it's the x cubed flipped over and the left goes up and the right goes down. So just think of x cubed and how its ends behave. What if the leading term has a degree that's even? And let's just think of our basic x squared. If we have an x squared with a positive coefficient, we know it opens up and both ends will go up. Both ends behave the same. If we stick a negative in front of x squared, both ends will go down. So if you know how x squared, which is an even function, or an even degree function, if you know how its ends behave, then anybody who has an even degree, whether it's 2, 4, 6, 8, the ends will behave just like x squared. So if the coefficient up front is positive, both ends will go up. If the coefficient up front is negative, both ends will go down. So we want to determine that for our polynomial functions. How will the ends behave? Okay, the print didn't come out very well when I imported this, so I had to go back and type that in, or actually find it on the other sheet and write those in. But let's use a leading coefficient test to determine how the ends would behave for these three polynomial functions. Now remember, your polynomial function has to be written in descending powers, highest power down to the lowest, and what you do is you just look at the leading term and let that determine how your ends are going to behave. So I see that the degree on the leading term is odd. So that tells me the ends are going to behave like x cubed. One goes up, one goes down. And since it's a positive coefficient, the right end is going to go up like x cubed and the left end is going to go down. So we could say it falls on the left and it rises on the right, just like x cubed. Let's take a look at this one. The leading term has a degree of 4, which is an even power, so that means it's going to behave like x squared. Since it's a negative up front, it's going to behave like a negative in front of an x squared. And we know if we have an x squared and a negative up front, then it flips over and the ends go down. We don't know what's going on in the middle. We're just figuring out the end behavior on the far left and far right. So we could say that it falls on the left and it falls on the right. Let's look at the leading term over here. The degree is 3. It's odd, so it's going to behave like x cubed. But since there's a negative coefficient up front, it's the x cubed that's been flipped over, which means it's going to go up on the left and down on the right if I were to flip over my x cubed, like I have written up here. So to describe the end behavior, I would say that it rises on the left and it falls on the right. That'll take care of end behavior. What we could do is we could put these in our calculator and see if the ends of the graph of the picture that we would get on our calculator would coincide with the decisions we made over here about falling and rising. I'll leave that up to you. Let's recall a statement that we had earlier in Chapter 2 about the word 0. Back in Chapter 2, we said a 0 is just another name for an x-intercept. And actually we saw that on our calculator. When we went to calculate or to find an x-intercept on our calculator, we went to we went to Second Calc and chose the 0 feature on our calculator to find an x-intercept. Well, for these polynomial functions, it's going to be important for us to find the x-intercepts, or as they'll be called in this chapter, zeros. Those are found by taking your function and setting it equal to 0, and then solving it. So we set f of x equals 0 in solving, and solving this equation may involve factoring and possibly the quadratic formula. Let's get a quick reminder of what that quadratic formula is. Negative b plus or minus square root b squared minus 4ac all over 2a. We used that back in 3.1. Let's work on finding some zeros of a polynomial function. Okay, let's look at finding zeros for these polynomial functions. I've had to again rewrite these because the document didn't import very well. But we have a negative x to the fourth plus 4x cubed minus 4x squared. And we're going to do some factoring to find the zeros of these polynomial functions. So let's recall some factoring techniques. We're going to take this polynomial minus x to the fourth plus 4x cubed minus 4x squared, set it equal to 0, and work on factoring. What I notice is there's an x squared common. I can pull that out. And remember, if you ever have a negative at the beginning of your polynomial, it's always a good idea to factor out that negative. Makes it a little bit easier for the factoring further if you need to. So if I pull out a negative x squared, I'm left with x squared minus 4x minus 4. Excuse me, plus 4. Make sure you change your signs when you factor out that negative. Let's go a little bit further. This x squared minus 4x plus 4 factors further into x minus 2, x minus 2. So remember, when you factor, when you're solving this equation by factoring, once the factoring is done, you set each factor to 0. So I'm going to set each one of these factors to 0. Negative x squared equals 0, x minus 2 equals 0, x minus 2 equals 0. Solving each one of these, let's take a look at this one. Negative x squared equals 0. This is basically asking me, what can I square and get a 0 as an answer? Well, that's going to be x equals 0. If I solve this one for x by dragging the 2 over, I get x equal 2. Add 2 to both sides, I get the same answer that I had there for that factor. Because the factors are the same, they give me the same zeros. So that would be my list of zeros by factoring. Let's work on factoring this one. So x cubed minus 3x squared plus x, we're going to set that equal to 0 and work on factoring it. I'm going to pull out an x because there's an x common. So I get x squared minus 3x plus 1. There's my first factor of x. This quadratic inside, sadly enough, does not factor. So if I have a quadratic that doesn't factor, I've got to jump into the quadratic formula. So let's pull out that quadratic formula I mentioned a minute ago. Negative b plus or minus the square root b squared minus 4ac all over 2a. Let's pull that thing out with this value of a, b, and c. And let's figure out what those values are. Now, I'm obviously running out of room, so you may have to do the arithmetic on your own. Let's see what this quantity is going to look like. Negative b is going to be opposite of a negative 3, so I'll have a 3 plus or minus. B squared, negative 3 squared will be a 9 minus 4 times a, which is 1, times c, which is 1, all over 2 times a, which is 1. If we clean this stuff up, I should get 3 plus or minus the square root of 5 all over 2. That doesn't reduce, so that would be my final answer. Well, I kind of ran out of room, so let me do this. And let's list out the zeros for this function here. I would have to take this guy and set him equal to 0. So my list would be a 0 and a 3 plus the square root of 5 over 2 and a 3 minus the square root of 5 over 2. Or you could write that as the plus or minus, but that would be our list of zeros for that polynomial function. So we start by factoring if we can. If it ends up that part of it can't factor, we may have to pull in the quadratic formula. What's nice about these last two is they're already factored for you. So if the problem is already factored, then all you have to do is set your factors to 0. It's taking this polynomial function, setting it equal to 0, which means we're going to set the factors that are already there to 0. We don't need to worry about the exponents, just the base here, those factor bases. One answer of -1, one answer of 3/2. Setting my factors here equal 0, x plus 1/2, x minus 5, ignoring the exponents right now, we get a -1/2 and a +5. Notice I didn't set this front part equal 0 because there isn't a variable with it. It's just -4. I'm not going to set more equals 0 because -4 is never equals 0. So it's not necessary when you have a constant up front to set it to 0, just if there would be a variable with it. If that were -4x times x plus 1/2, then the -4x would be set to 0 and solved for x. Only if it has a variable. So here's the list of zeros for that one. Here are the list of zeros for that one.